after lunch, you know, it's always a challenge to give a talk while you are fighting with your sleep, and I am trying to tell you something here, but let's see how it goes. So like mentioned, all this work was primarily done at IIT Bombay, partly at IIT Delhi. I spent 7 years at IIT Delhi, but 18 years at IIT Bombay. BITS Pilani have been here for about 8 months now, so it's not really much. I will talk about the lot of research is happening, but how do we develop, or how the translation research basically. So my talk is all focused on how do we translate research in our academic institutions, what is coming in the way. So despite so much of great work happening, we don't seem to be doing very well when it comes to product innovation. Yes. So my talk is primarily focused on what do we need to do for increased translational kind of research in our academic institutions, because I see so much of talent, so much of great science happening, and how do we connect it to the problems in the society. India, if you see, there are over 1,000 universities now. There are 135 institutions of national importance, all IITs, triple ITs, NITs coming together. And the gender ratio is pretty good, 50-50 in the higher education sector. Our gross enrollment ratio is pretty low, so but that's what NEP is targeting, to take it to 50%. And if you are wondering how many PhD students are there in our academic institution, this is a slightly dated kind of a number, but growing at 10%, over 200,000 PhD students. Now at this rate, it would have crossed 250,000 now, and close to 300,000 PhD students are currently pursuing their PhD in our universities. So these are the statistics, and the current status, if you see, India ranks third in the world in scientific output, seventh for highly cited scientific papers. This is data from MHRD. I'm hoping that they would have taken it from Elsevier and one of these agencies. And 40th for innovation. This is the innovation ranking which came out a couple of weeks ago, 40th for innovation, and 54th for percentage GDP allocation for R&D among the 130 countries. We ranked 54th now in terms of money spent on R&D. We are not spending enough money. And 66th for academia industry collaborations. So I think this tells the full story, that while we seem to be doing excellently when it comes to research, and even in terms of quality of research, there are the good institutions in the country which are indeed doing pretty well. And but the problem is with all these other kind of metrics, innovation, percentage GDP allocation for R&D, and academia industry collaboration. So I think these are the parameters which we need to essentially improve. Otherwise, there is nothing wrong with Indian academia, nothing wrong with what's happening in the country. And of course, China and US are way ahead, and 20% of global share for China, 16% for US. India is just about 5% right now. But I think if we give more money, institutions, JNC for example, is like 45 faculty. JNC should have 200 faculty. With the kind of excellence that exists in some of these institutions, if only we can scale up these institutions, I think our percentage share in the global, the number of publications, that will definitely go up. But I think, I don't know why such good institutions are kept so tiny. And I think the whole scalable model exists, but we are just not grabbing that opportunity, which is unfortunate. India saw a growth rate of one of the fastest growing countries in terms of scientific publications too. The world average is only 4%, so even that we are doing very well. And this is the data which I had some access to, something done in DST. So obviously, even from these rankings, you can see that per dollar spent, Indians are writing more papers than anybody in the world. So I think that credit should go to all of us, that we are experts at converting any money that is given to us into excellent research publications. So that we can do very well. But what in my opinion is majorly missing is the impact and translation of that knowledge into wealth. While we have become experts at translating the funds given to us into knowledge, but we are very poor when it comes to translating that knowledge back into wealth. So that is where I guess we need to put our efforts now as we go into the next phase of our growth. I have also done some of these searches on Elsevier, on Scopus and other parameters. So we are doing pretty well. In any area you take, quantum or nano or bio or sensors, we are in the top 5 in the world right now. And even in terms of quality metrics, we are now at the seventh position, 2018 to 2020 average number of papers, highly cited scientific papers category. We have displaced many of these countries now. So I think the quality is also growing, and out of the volume of research happening, obviously there will be some good papers too, which is essentially helping us. But if you look at even the unicorn story, the billion-dollar valued companies, India is again doing very well. There are like 107 unicorns or so. In fact, BITS Pilani alone has produced about 15 unicorns in this list, and many, Swiggy and many of these companies have come out of the BITSians. So I think India's story on the unicorn front is also good, but these are all in the IT, e-commerce, fintech kind of a space. None in the technology space, which has reached that unicorn status as it, which is not even close to the unicorn status right now. Many of the companies, we have all incubated are in the 50 crore to 100 crore kind of valuation. So for them to achieve 8,000 crore valuation will be a tall order. I don't know whether in our lifetime we will see anything like that happening. So that is the story of our unicorns, all IT and e-commerce, which is good. But none is deep tech based, mostly business model innovations, not technology innovations. But this is where academic institutions need to play a role. And also, most of these unicorns, if you see, there was a nice study by Stanford University professor, and where most of them, I would say 99% of them, are started by the undergrads. It's undergraduate students who are starting companies now and growing them into unicorns. At the undergraduate level, they will not know any technology. They would only be able to think of some nice business model and make a company out of that. Most of them are these aggregation kind of models. Somebody building an app for dhobis, somebody is building an app for carpenters, somebody is doing that. And if they are lucky, if they are first in that kind and have the right investors, they make it achieve that unicorn status. But beyond that, nothing, which you can call a great technology innovation there. But academic institutions, they too, therefore need to play a role if we are talking of deep tech innovation, the deep technology innovation. There are three aspects to an academic institution. Education, of course, we seem to be doing well. Research, again, we are doing very well. We have seen those statistics. It's the innovation where we are lagging behind. What is innovation? In my presentation, for me, innovation is generating value out of research. So you have done 100 papers, written 100 papers. What is the value out of that research? So citations is all research. So, but innovation is generating value for research. Somebody paying money, for the IP that you have generated. That is what we need to do. And that sort of innovation in the deep tech space can only come out of our top academic institutions. So therefore, connecting that academic R&D to innovation, in my opinion, is what India needs to do very aggressively, very prominently, and with all the force that we have. And so I think again, R&D ecosystem inadequacies in India. Why is it not happening? Why it has not happened? There are multiple reasons. At least, I have served as director IIT Delhi for 6 years. In 6 years, I have seen, one bolt after another coming from some ministry or the other, creating, disrupting the whole, piece for the director and for the faculty. And one of the things is there is never enough money in this country. Whatever you want to do, we are at the bottom of the table. And as you can see, the below us are Pakistan, Philippines, Sri Lanka, and Venezuela. So otherwise, we are just not spending enough money as a percentage of GDP, which is the biggest challenge. Everybody has been complaining, but nobody is listening. And even I was so shocked to see that the finance secretary of the country, goes to press and says, spending money on higher education is putting money down the drain. That's what the finance secretary of the country is saying. So it's a sorry state of affairs right now. And I hope somebody wakes up and convinces the government to spend more money for R&D. The second thing, even in terms of purchase parity terms, one of the things that people say is, no, but less money doesn't mean anything. We cannot compete with the Western powers, which are all very rich and all that. So this is a purchase power parity terms. Our investments in R&D, right? It's a per capita gross expenditure on R&D in PPP terms. Even there, India is the lowest. Below us is Indonesia and Russia. They are not Russia. Which other country? No other country. Only Indonesia. So we are here right now. Even in terms of adjusted kind of a currency. This is the problem. And the second problem is we are not protecting our IP enough. India should be filing more and more patents. When I joined IIT Delhi as a director, IIT Delhi was filing 15 to 20 papers per year. And of course, during my time, we emphasized why we need to file more patents. And now IIT Delhi files about 200 patents per year. BITS also, great research institution, lot of research happening, writes about 2,500 papers every year, but files 10 patents every year or 15 patents every year. So I think that papers to patent ratio, in Western countries is pretty high. For example, in nanotechnology area, I was looking at this data. India in 2019 wrote 15,000 papers, ranked third in the world, and filed 54 patents. In the same year, US wrote 23,000 papers, 24,000 papers, filed close to 5,000 papers. So for every 5 publications in the US, they are protecting an IP. In India, for every 300 publications, we are protecting an IP. So I think if we are not even protecting our IP, there is no startup, there is no technology transfer, nothing will happen. We have let that whole knowledge out now. Anybody can use and sell it back to us. So I think protection of IP is very important, and we all need to be filing more and more patents if we ever want the translation to happen. Because without IP, there is no startup. In deep tech space, if you don't have patents, no investor will even touch you with a barge pole. And therefore, if you are not able to do that, even if you want to license this to company, what do you license it? I mean, if you hand over a paper, they are not going to read the paper and make a product out of that. So I think filing patents is the first thing that we need to do, and need to do it much more aggressively. So that's one thing. The second thing is, this is my informal survey, how do we choose research problems in academia, right? I mean, at least I spoke with all my friends in academia, depending on which institute you are talking to, anywhere from 70 to 100% of problems originate in library, and they also end up in library. So the way PhD students pick up problems is what I looked at. The PhD students, at least 90% of PhD students in many of our institutions pick up problems from the library out of that literature review that they do. I think if you keep on picking problems from libraries, you can do great research. There is nothing wrong about it. But since this talk is about innovation and translation, I think the translation kind of an activity won't happen. So that is one problem. But ideally, we should be picking problems from observing issues in the society through more immersion programs, rural internships, our humanities departments acting as a window, to the science departments, engineering departments. I think, that connect with the society needs to become better. And if US does it very well. The Morrill Act, 1857, the land grant university model is all about connecting US universities to societal problems. That has transformed US universities into centers of excellence. In India, that has to happen. Connections with industry, I showed you the ranking. There's hardly, any industry, doing anything of any value with academic institutions. Even the strategic agencies, all of them have created their own laboratories, and they have no motivation to work with academia. So that's again another problem. And I think these are the kinds of things. So unless we move, a little bit of our research away from library-based kind of things, pick up problems from society, pick up from the industry, pick up from strategic agencies, I don't think, that relevance will ever arise out of what we do. So we are great researchers, but the kind of problems we are working on, are not the ones where you can translate anything significantly, outside the institution. So this is one big challenge. So better connect with society, industry, and strategic agencies. But why would it happen? It won't happen just by wishing for that. And the industry, I will talk about it a little bit more. And I think, we need to have policies. We need to have incentive schemes. With the industries need to get some tax incentives. Industries need to have a policy mandate of spending some percentage of their, revenues, or, whatever they have, in the academic institutions. Unless government dictates that, I don't think industry is ever going to wake up and then start investing heavily in the academia. So I think some policy push is urgently required for industry to connect with the academia. So having said that, another fourth problem that I see as very significant is top talent not doing deep science. So even in our institutions, they just want to do the only science, that is computer science. Other than that, nobody is interested in any other science right now. And this is again a big challenge, because all these great innovations that have come about, if you take this mobile phone, I can name at least a dozen Nobel Prizes which are essential to build this mobile phone, from memory to display to camera to wireless technology to battery to processor to polymers. Every component of mobile phone has got a Nobel Prize. And without that emphasis on science in this country, everybody wanting to do computer science and doing only that, I don't think any great innovation will happen, because all technology is built upon science, and if you are not doing great science, I don't think there will be any great technology that will come about that. This is another problem. The another fifth problem here is the missing this valley of death. The university research often ends up at a technology readiness level, which is proof of concept 3 or 4. This is where university research ends, and the industry, the commercialization begins to happen at 9 kind of a level, 8 to 9. That is when you start seeing these people paying money for the products that you have developed and all that. Now there is this valley of death. A faculty member will develop things up to a prototype, makes a nice aluminum box, which he or she demonstrates, which seems to work very well. You go to any laboratory now, you see a lot of such aluminum boxes, lot of such demos. But what next? The next phase is, what is the valley of death right now? And there is no agency in this country which is willing to take up that research, put efforts, put resources, develop it to the higher TRL level, and then translate it to industry, or let an industry take over the technology or anything like that. There is no agency in this country which is bridging this gap. Ideally, if you ask me, CSIR must be doing that. Some CSIR labs, their only job needs to be to look for this IP in academia, work on it further, take it to the higher TRL level, let the industry get interested in that. That is what CSIR labs ideally should be doing. But then CSIR also awards PhDs, and they are all competing with us. And I don't think we have lost that bus now. And in many countries where things have worked, there are institutions, there are those processes which take that IP and bring it up to this level. So these are the kind of institutions that we need to create, which can work as an interface between academia and industry. So this is again something that is missing. And I will skip this. And then the other problem is the siloed higher education system, because products, any problem oriented research doesn't come with a disciplinary tag. Right? If you want to solve air pollution problem, which discipline will it come under? The farmers problem, none of these problems will come with a disciplinary tag. They all are multidisciplinary, and making these people from across the departments itself is a big challenge. Making them work across the institutions, again, there are no national schemes to promote interinstitutional kind of collaborations. This is again another problem, where we have such excellent institutions but focused on in a very narrow area, and that is again hurting us very badly right now. So we need more schemes for interinstitutional kind of collaborations, because creativity is all about connecting the dots, and also discipline oriented, including our funding models. Who actually funds our research? Our research, 90% of funding comes from DST, right, or SERB. And DST doesn't have any problems of its own. What problems DST scientists can give you? You go with your problem, defend your problem to all of us. Sometimes you are on that side, sometimes on this side. So we defend to each other, and we get money. So we have created a nice vicious circle where we define our own problems, we solve them, we're happy. So nobody needs to know what we're actually doing. Imagine a situation, I was hoping that NRF would actually do that. What should NRF ideally have done? NRF should have connected academia with all the other ministries, the line ministries, the allied ministries. They pulling in resources into NRF along with the problem statements. If NRF had done that, if NRF had pulled all the problem statements from all these ministries along with the funds, and then gave problem statements to the researchers saying that this is a problem I want you solve, now you provide a solution to that, I think things would have been greatly or vastly different in the country. But NRF is another name for SERB now, so I don't think even that is happening. So therefore, I think this interministerial collaborations and these ministries collaborating with NRF or SERP or DST is the need of the hour. And in the absence of that, I think as long as we pick up our own problems and get funded, I don't think we will ever connect with the society. So these are the funding problems. These are the multidisciplinary challenges. So some of these need to change. As if these are not enough now, I recently called it 4G. the GFR, GST, GEM and GT. I think, I saw each one of them during my time as the director. And if you don't know what GT is, this is the global tender inquiry. And if you want to buy any equipment which is 5 lakhs to 200 crores, you need approval from the Secretary Ministry of Education. Now, what would the Secretary Ministry of Education do when it comes to buying some equipment in a scientific equipment, an SEM or TM in an IIT? Nobody knows. But then, this is what the government has mandated now. The GFR is a nightmare. The GEM is another, whatever you want to call it. The single treasury account is a disaster. They said that as many projects, as many accounts now. The curbs on imports, the global tender inquiry, you need ministry approvals. In IIT Delhi, it takes 11 months now to buy an equipment. 11 months. I mean, how much of time a faculty member will have to, all the time goes in just buying that equipment. GST on scientific equipment without any notice. They said, now this GST will apply. Now DST raises hands, everybody raises hands. Where do you, bridge that gap? Again, people were running pillar to post to get that bridge funding to cover the GST, subcritical funding, disproportionate expectations. In 3 years, you should have solved a problem, sold it, and made $1 million kind of money out of that. That's what every bureaucrat expects you to do. Lack of motivation, scrapping of all recognitions. I don't know who told the government that, we are over recognized. And then the leadership challenges, I don't have to tell you that. The fractured funding for research and innovation, the DST funds you for research, right? Now, if I develop a product, right, if I start a company, then I am untouchable because DST will not touch a company. DST funding can only go to an academic researcher. I mean, you should be funding ideas, not the institutions, not where the idea is coming from. We are not funding ideas. We basically fund the institutions. I think that is again a major problem. NRF, I have been telling them, fund ideas, not where the idea is coming from. And but I think many things, you can. I'm sure you will have a longer list of these problems. But this is what I have directly experienced. So I thought I will compile all of them in at least in one slide. And then so therefore role of HEIs, three aspects: education, knowledge generation and innovation. How does knowledge become innovation? To me, knowledge will become innovation when there is relevance to what you are doing. So you have picked a problem from a place, where it needs to be solved. And then you put all your resources and then develop a solution and translate that. That relevance is very important. And great people, but working on problems which have no relevance to anybody right now. The industry anyway is not talking to us, and nobody expects anything from academia. Our biggest challenge is nobody expects anything from academia other than just graduating some students year after year. So that in that situation, how do you find your relevance is indeed a big challenge for the country. And the delivery, now where I see great research happening, where they have come up to TRL 4, but everybody is struggling. So now how do I manufacture it? Where do I go for manufacturing? If I start a company, who will fund me? I think all these are challenges now. The delivery is another problem. So these are the kinds of things. So now that I have given you, depressed you enough after lunch about what all is happening or not happening, the next, I think I have maybe 10 minutes now. In the 10 minutes that I have, let me tell you what I have been doing. So I have, my areas of research are in nanoscale devices. Now, one thing I did, fortunate for me was, I worked at places where I had strong industry collaborations. I brought all the collaborations to India. So I started working with the same company. So we did a lot of good things. For Intel, for example, we transferred at least a dozen patents, and Intel made tons of money out of that, out of our IP, which we jointly filed. They recently wrote to me saying hundreds of millions of devices, have been using that IP that we generated in academia. So that kind of talent is definitely there in our academia, but our Indian industry is not really using that. And then the sensors is another one of my areas. And then I, of course, combined sensors and CMOS, but I will talk briefly about my sensors research. I won't, get into too much of scientific details, but I believed in doing research for societal kind of a impact. And so I chose sensors because I work on CMOS. That was my primary, bread and butter. I did my PhD and worked on CMOS for a very long time. But I realized that you can't do anything in CMOS when it comes to India. There is not a single semiconductor industry. What do you do, developing all those technologies? Of course, Intel benefited from that, but I wanted to do something in the country for the country. And so then I started to switch my areas to sensors, IoT devices, and then look for a problem, where I can develop a solution. But when you are looking for problems, there are enough problems here. As I always say, all the world's problems are in India. I mean, if you are looking for a problem, you don't have to go to an American journal and search for a problem. Just look around you. Agriculture is a problem, healthcare is a problem, security is a problem, energy is a problem, water is a problem. Each one of them, you can spend your lifetime developing solutions. So then I started to look at what can I really do. I'll skip that. It's not really needed for this audience. So I started to look at what can I really do in order to develop a complete technology and a solution to a problem. But I also was very conscious of the economic levels of Indians, right? If you develop a solution which is expensive, even if you have spent 10 years, 15 years of time, nobody will buy that. So you have to make it very price conscious. Indian market is very price conscious, so therefore you need to keep the price points in mind right from the beginning. That is one difference which I did in my research, which not many people do. Whenever I developed a technology, I had the end goal in mind, right? And then I always were conscious about, if I use this 4 crore tool to make my device, can I sell it for 100 rupees? I won't be able to sell, because if I use such, if I require a 100 crore facility to make my device, I need that 100 crore facility to go out and set it up. And in this country, nobody is going to give me 100 crores of rupees to establish a facility for a company, and I won't be able to raise that kind of money. So I was very conscious from the beginning, what would be the cost of that entire technology, what sort of facilities I will require, where can I do that. So this was one thing which made my research more interesting, not less interesting, because the very first problem we took up at IIT Bombay was a low cost cardiac diagnostic system. We saw that there were one of our colleagues fell ill, had a heart attack while taking MTech interviews, and then we took him to the hospital, and then we started having discussions with the cardiologists, and that is when they actually approached posed us a lot of interesting problems. They said, why don't you guys develop some simple tests like the protein test like troponin I, CKMB, myoglobin. Can you have simple diagnostic device, point of care device, where I put a drop of blood, I can get all these marker concentrations right, bedside, and I can use that information to decide what to do with the patient, because so many people come with a chest pain and I cannot be treating everybody as a cardiac patient. And so how do you differentiate between a simple chest pain with a cardiac problem? I think these were the kinds of things that they posed. And then we came back, and then we formed a multidisciplinary team, and we said we will develop a system which can detect at least two of these markers, the troponin and CKMB kind of markers, the cardiac proteins. And so our goal was to develop a technology for detecting these two markers with a drop of blood. And then we started with a top-down kind of a design. We said, what do you need to actually detect these proteins bedside in the hospital itself? So you take the blood sample, you need to filter it out. You don't need the whole blood for this. So you filter it out, you take the serum, you have the microfluidic channels, you have the biosensor array, and where two sensors will be integrated with the microfluidic channels here and the blood separation, plasma blood separation right on the chip itself. And this entire thing will be disposable, and then a small tabletop instrument which will actually show you either the concentrations, or even qualitatively, if your troponin is high, that's okay for the first purpose. So we wanted to develop a system like that, and we started a top-down kind of a thing, right? The way industries would actually do that. Then we approached faculty, those who were doing microfluidics. We told them, can you help us integrate your microfluidic platform with our sensor array? Those who were doing the kind of filtration kind of technologies in the mechanical department, then we involved them in the project for blood plasma separation. And many people got into this area out of curiosity, out of because this posed a challenge to them, that we want to develop a complete system. You contribute your part, and then we contribute our part, and finally let us develop the complete system. And then we had the price point in mind from the beginning. We said the chip, the cartridge should cost about 100 rupees. So therefore you cannot say that I will use gold platinum in your materials, you cannot do any of that. So you have to always choose very low cost kind of technologies for making that. And then we realized that even silicon will not be useful for some of these technologies because these are all disposable, and silicon is a good material but an expensive piece of material. For disposable applications, silicon will not work. So then we started to actually use polymer cantilevers. So we started making piezo-resistive polymers. These are all the piezo-resistive polymer cantilevers. We did a lot of interesting work in this and we published many papers. But for us, the reason for choosing polymers was not because we wanted to, write papers in that area, but because this was a need for us. So because polymers, you can do very low cost processing and very cheap materials. And if you can integrate piezo resistors into that and do this sensing antibodies you quote here, and they bind to the cardiac proteins, that antibody antigen binding is what you detect electrically because there is a piezo resistor integrated here. So the entire problem is to make such a piezo resistive polymer device and at a very low cost with a very high sensitivity. So when there is a reaction here, there is a stress, the stress gets converted to strain, and that is what you are measuring as a delta R kind of a value. The entire goal is to, for what deflection are you getting what amount of delta R. So that was all what was involved. So we did a lot of interesting research combining nanoparticles, polymer composites we embedded nanowires, zinc oxide nanowires between the two polymer layers to make it into a cantilever, and then we used a very innovative technologies. All of this research is published, you can find them or I can share those papers with you. We also used graphene, because it was known to be a good piezo resistor. It had a high strain gauge, so gauge factor, so we started using even graphene for its high gauge factor. And then we also experimented with poly cantifets, the cantilevers, polymer cantilevers with organic transistors embedded on them for strain sensing. So we did a lot of innovation there. I'll skip that because I have run out of my time. And so we, after doing all of that, we actually demonstrated and published that for every nanometer of deflection of the cantilever, which is arising because of antibody binding to an antigen, how much is the change in delta R, the ppm per nanometer. So we showed that our work was 128 ppm change in delta R for every nanometer of deflection as compared to what was available in the literature. So we actually published saying that this is a world record for delta R by R per nanometer of deflection. And then we started developing electronics, because at the end of the day you are measuring delta R values which are pretty small, which are like ppm. You are measuring a few ohms in a mega ohm kind of a resistor, and because of temperature and other things, that itself is a research. So we also wrote excellent papers on building very sensitive electronics for delta R measurements. And then we went to IDC, the Industrial Design Center at IIT Bombay, and then we actually built our very first system, called it iSense, standing for Infox sensor, developed under the iSense project from NPSM and NPMOR. It's a DRDO kind of a scheme. And then this is actually working very well. It was able to detect two markers, and then we showed a proof of concept. Then we were very excited, and then we started a company because we wanted to start a company, and we were very young at that time and very novice. So we started this nano sniff in 2011, and we then transferred the technology to them, and we said, now you take it forward and develop it into a complete platform. The problem was, then they started approaching hospitals, but no hospital would talk to them. And then all the hospital trials were costing money, and all these doctors individually were very excited. But when they sit on a committee, on ethics and other things, then the real problems start. We couldn't move really forward. I mean, one hospital agrees, but then it was a bit of a challenge. How do you make, large number of these devices? That funding also was a challenge. From 4 or 5 devices, how do you make hundreds of devices? That facility was also not available. So we got stuck there. And fortunately, around that time, Dr. Baldev Raj, who was director of IGCAR, and he learned, when I made a presentation to Professor CNR Rao, he was there on the committee in the Nano Mission, and he said, you seem to have an excellent cantilever platform. Why don't you use it for explosive detection? He said, everything can remain the same, but then you only need to coat these cantilevers with molecules which can selectively bind to vapors of explosive. And since rest of the things are already there now, so you use this platform for detecting explosives. Now you start working with the chemists. And then we started working with many chemists in the country. We had brainstorming sessions and everything. It was funded by PSA office at that time. So we explored a lot of molecules and worked with many good chemists. We wrote many papers, right? but then all work very nicely in the laboratory. You take it out, nothing works. Then the humidity, the moisture, everything kills these molecules, and the binding efficiencies were poor. We could never achieve the selectivity that we needed out of these kind of chemical coatings on the cantilever. Then we said, can we do a electronic nose kind of a platform? Instead of one cantilever, one coating, can we make multiple cantilevers and multiple coatings? And then we again started working with chemists. We looked at multiple coatings for the cantilevers and see whether you can detect a pattern, when a binding happens on the surface. So we started doing pattern recognition, and this is more like the XNIF, the nanos, the kind of the platform which is known as the electronic nose kind of a platform. So we developed this entire pattern recognition algorithms, made it into a system, had multiple cantilevers with multiple coatings. This also worked very well, but then it would have efficiency of about 80%, and beyond 80% in high humidity conditions, and even in places, for example, in Kashmir kind of places, when they place a bomb, right, the terrorists also put a lot of cow dung and create a lot of smell around that. And many of these platforms would get confused if there is something very very strong kind of a odor there. So these things did not go too far, and so though we were very excited and wrote again lots of papers, but when it came to applications in the field, it did not meet the requirements. So we were very depressed. We did not know, how to move forward. And in the airports, if you see, they are all using mass spectroscopy systems. There is one FIDO system from MIT which does that, but we wanted to be unique and different. So we then one fine day when all of us were discussing, we had a great idea. I mean, that was a game changer for us. We said, what is the property of an explosive? Property of an explosive is to explode. So we said, can you actually collect a few nanograms of this material and practically and literally explode it? How do you explode an explosive? You have to give it a thermal shock. So you build a tiny micro heater which will give that thermal shock to, let's say, a few nanograms of explosive, and these are all high energy materials. The energy released is what you sense with a temperature sensor, because each explosive will have a thermal signature. So you are capturing that thermal signature with pattern recognition, with AI/ML kind of techniques. Now you can now track their thermal signatures and identify the kind of an explosive. Non-explosives will have a totally different thermal signature as compared to explosive. So we wanted to do that. We actually wanted to explode and detect the explosion. That was as simple a sensor as it can get. It's all physics. There is no chemistry here now. And then, but how do you explode the material? So you have to give it a thermal shock, as I said. So we started building these tiny switches, tiny micro heaters, because you have to reduce the thermal mass so that you can, in milliseconds, you can raise temperature from room temperature to, something like 400 degrees centigrade. So we started making these devices at IIT Bombay in the nano fabrication lab. We did again a lot of good research here, wrote many papers, and finally we were able to build a system. I have a small video, I will just play this. This actually captures what.
Behant Technologies, an IIT Delhi incubated company, and NanoSniff, an IIT Bombay incubated company, jointly manufacture and launch NanoSniffer, an advanced and affordable explosive trace detector, screening visitors and passengers for explosives at various public or crowded spots have become the norm due to the increase in the terrorist activities around the globe. Every luggage and person passing through the security checkpoint is tested by the security officer to check whether they have traces of explosives on their surface, skin, or hair. NanoSniffer proudly claims to be the first explosive trace detector in the world using microsensor technology. The microsensor of NanoSniffer is made using micro-electromechanical system, MEMS technology in semiconductor fab. The sensor uses fabrication techniques such as lithography, etching, deposition, spin coating, and finally released to the microsensor. The core technology is protected by patents in the US and Europe. All of our actions leave trace behind, which is then screened by the security personnel. The security has to concentrate at the sampling areas that are likely to be touched by hands. In the case of a bag, this will include handle, buckle, and zipper. Post-sampling, the swipe is inserted into the system where microheater subjects the particles into rapid heating. In case of explosives, this triggers exothermic reactions which are picked up by the integrated temperature sensor of the microheater thereby landing each compound in its own thermal signature. The algorithms use these signatures to distinguish between explosives and non-explosives. Further analysis of the algorithms help in categorization into the appropriate class of explosives. The follow are few nanosniffer features. It is the first microsensor-based ETD. It detects and identifies explosives in less than 10 seconds, identifies and categorizes explosives into different classes, can detect ng quantities of explosives traces. It detects all classes of military, conventional, and homemade explosives.
I think
It is portable and
I think the good part of this technology is, because there is no chemistry there, it can detect anything that explodes. So that way, with the thermal signature, we can classify it, and this is working very well now. And technology has been developed, and now this has been commercialized. In 2020, we launched it as a product because it was developed with government funding. The minister had launched it, and then we now have it in multiple airports. In fact, 11 airports in the country are currently using it, and we have no competition because this is a completely proprietary technology, and things are looking good now for nanosniff, and they are selling many more systems now. And then we further developed it into an IoT node. I'll skip this because I have run out of time. And then we also developed the piezoelectrics, so that if you place these sensor in a bus or a train, can you power it from the vibrations? So that is how we use the piezoelectrics to power them. And we wanted lead-free piezoelectrics. So now we developed the lead-free, and we recently wrote a paper in ACS Energy Letters. Some of these are perovskite-based lead-free materials. And so then after that, I started working on agriculture. So now that technology is out in the market, many airports are using the nano sniffer. Now I moved to agriculture about 6 years ago, and with a exactly similar approach, develop the complete system, do research, but develop the complete system. So now, in fact, last year we launched this product, NutriSense. It can do NPK and soil moisture and the electrical conductivity. So this is also in the market now. We have multiple patents on this device, and we are testing it now in the field and training villages for soil testing. And essentially, we are developing sensors for all the macro nutrients present in the soil health card. Government of India has distributed tens of millions of soil health cards. So we are developing sensors for all of these materials. Many of these technologies are now in the market. We started a company, Soil Sense, at IIT Bombay. This is my second company. So they are doing very well. They have this suite of products. The NutriSense is their major product right now, which is selling very well again. They are even exporting the technology. And so this is how it all began. So identify a problem, bring a multidisciplinary team, patent the technologies early on, and use startup route to get the technology out into the market. So it has worked very well. NanoSniff now has made a name for itself, and they have now it's no longer a startup, and the explosive detector is their major product right now, and they are selling everywhere. And Soil Sense is a young company. It's a 3-year-old startup now, but they also have technologies in the market, and they are there in at least 5 states. They are selling it directly to the farmers. I think therefore this innovation, research to innovation at the individual level, the top down product oriented approach is the key. On the platform you can write tons of papers. I have written all my papers on the platform, but then you protect the IP as early as possible, and then you, with the help of students, the right kind of students that you come across, you can take it to the market and commercialize that. At the institutional level, again, we have to build those multidisciplinary teams, an idea factory kind of an approach. I think that is where the ideas will come from. So I think otherwise our institutions are very homogeneous in nature. That's a big challenge. And then create this ecosystem for deep tech startups in the institution to fund them. So this is again something which at least I had done very aggressively at IIT Delhi, and this is something I am doing again in BITS Pilani. So we have launched multiple schemes for faculty to turn faculty into entrepreneurs. We started this PhD Drive program, an entire PhD program where we want the PhD students to start a company eventually. And this is a technology program, not a management program. So this is again something that is receiving a lot of traction. And national level, I think we need to create these labs. I don't know what you want to call them, but the TRL 4 to TRL 8, That gap exists. Otherwise, I could do that because I have enough networks and connections, and I can pull many things, but not every faculty member will be able to do that. So I think we have to create these labs in between, which can work with academia, take these technologies, deliver them to the develop products, and either through startup or technology transfer to industry, they can actually get it out into the market. I think these are the need of the hour for the country right now. I'll stop here. Thank you.